Okay, then off we go. So, okay, so today we're going to do a couple things, and then maybe we'll even start the next lecture if we go fast. But it's going to be sort of similar in generalizing some of the stuff we did with merge sort. So, all right, so we'll just start with the basic problem of selection. Okay, so I give you in the simplest case, I give you a set of numbers in a list. They're not sorted for you, and I say find me the median. Or find me rank 100, meaning the 100th smallest number. Okay, the rank k, the simplest case is the median. So what would be the median in those numbers? 56? All right, anyone else get 56? 56, we got 164. Anyone else get 64? 56 would be this one. So there's 11 total, so there should be 5 smaller and 5 bigger, I guess. That's smaller, 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 smaller. So I guess it's probably the median. Okay, so this is only input of size 11, and everyone squinted, and I feel like if I didn't put the check marks underneath, it wouldn't even be that obvious that it was the median, right? So, even this problem is a little non-trivial, and our goal is to do it fast. But what would be like a natural algorithm to solve this? Yeah, so the easiest thing is just to sort the numbers, right, and then look up the kth. Now take n log n time. We're pretty happy with sorting, great. But our goal is to actually try to do even better than n log n. Okay, so we're going to try to pick out any arbitrary element without actually sorting the entire array. But at some level, we've already just did, right? We didn't sort the whole thing. We were able to verify it without sorting it, but yeah. Okay, so, all right, how are we going to do this? Well, I guess we'll do a recursive algorithm. So I'm going to just force us to state some kind of recursive spec, right? If I want to design a recursive algorithm, I just want to write a sentence that states the input, the output, etc. Sure. So just give me one. Choose a name, choose an input. Select. Yeah. Oh, sorry. I spoiled it. Is that, hmm? Okay. So simple enough, right? Okay. I give it a name. I gave it select. Takes as input k and your set of elements because we might want to recurse on subsets of elements, right? So it's good to have a as a parameter in there. And so give it an array and some rank k. We're going to get the rank k element. Okay. Often we're just going to restate the problem. Sometimes we'll do something more subtle, but often at the very least, that's the first thing you should do, right? And then see if you need more bells and whistles. Okay, so now we know what we want to implement. Now we're going to try to implement it. But actually, the algorithm we're going to work towards is going to be a bit non-trivial. So let me try preparing this in a sort of incremental way. So, okay, so in general, we're going to try to get the kth element for an arbitrary k, input k, right? But suppose I told you that you could find the median in linear time. Okay, so I gave you a black box. It's a magical thing. We don't know how to implement it. But it's a special case of our problem, right? So of course, if you can implement select, then you can implement median. But I'm asking the opposite question. If you can implement a median really fast, could you implement select fast? Okay. Any ideas? Yeah, it's the special case. Yeah, so I give you access to a subroutine that will only return the median for you. And can you take this specialized algorithm and do the general case? That's the question. So I saw a lot of nodding. So how might you go about it? Okay. Okay, so sometimes this idea is called a pivot, but I think this is what was described. So use a quicksort like thing, right? So first step, given our unsorted array, we'll compute the median, right? Okay, and then we're going to take the median and we're going to divide the input into everything smaller than the median and bigger than the median. Let's say to simplify our discussion, we'll assume everything is distinct. Okay, so smaller than the median, bigger than the median. Yeah. And if you're looking for like you know, and then you just say, oh, k is either going to be smaller than n over 2 or bigger than n over 2, and that tells you which side to go on, right? So you figure out the appropriate half. Maybe it's the second half if k was bigger than n over 2, and then you're just going to recurse, and you're just done, right? I didn't draw out all the recursive stack. You just recurse and you're done. You do need to make sure, for example, when you go on the bigger half, right? The rank k for the original array is now going to be like rank k minus n over 2 if you're just looking at the bigger half, since you're throwing away n over 2 elements. Maybe n over 2 plus 1, depending on, but this kind of thing. So is that it? Okay, so that's a clean and simple idea. This would be like pseudocode, but I feel like it's not very helpful. It just makes it look more complicated than it is. Okay, but I think we're on the same page. Get the median, split in half, recurse on the appropriate half. Okay, all right. Or maybe I should at least mention one trick I sometimes do. I have some very lazy base case. If n is less than equal to 10, you could go all the way down to like 0, 1 and be very careful. I just wrote if n is less than equal to 10, you brute force, by which I mean sort, find the exact k. Yeah, then I don't have to worry about like, oh, is 1 enough, 2 enough? 10's fine. Okay, so good. So what would the running time of our algorithm be, assuming that median takes on? How would I model it first? Yeah, so the median takes on time, plus you do a recursive call of size. Yeah, something like this. Okay. So yeah, this you can just see, like, even if you did a recurrence tree, yeah. Oh yeah, yeah. I didn't do that slowly, but that's a great question. So step two, divide the input. How long would that take and why? Linear. And what would you do? Yeah. So I have the median, and I'll take every number and just compare it, put it on one side, compare it, put it on the other side. So that's just n comparisons. Yeah. Good. Good to slow me down. I get too excited. Okay. All right. So like, I don't know, for the sake of uh, teaching, if you made a recurrence tree, your problem size are going down, down just by factors of 2, right? And you say, okay, how much time do I spend on the top level? That's n. Second level, n over 2. Third level, n over 4, and so forth, right? So like, what's 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32? Yeah, oh, I didn't include 1, but if I included 1, then it would be almost 2. Without 1, it would be, of course, 1. Yeah, so 1/2, 1/4, and one way to think of that one in particular is you start with 1 and you keep removing half of what's left, half of what's left, half of what's left. Okay, you've probably done this before. So your overall running time comes out to, you add this up, you spend n work. Okay, you got some linear time algorithm. Great. But of course we cheated, right? I assumed you had an exact algorithm for median. Now you know actually the two problems are roughly the same. If you have an algorithm for select, of course you have median, but if you have median, you actually have select in linear time. Okay, so we don't have a linear time algorithm for median. So step two is I'm going to try to relax this a little bit and say, suppose you only had a linear time subroutine for an approximate median. Okay, So I promise you, this algorithm is not necessarily going to return the perfect median, but it's going to return something from like the middle 80%. Okay, it might have rank like n over 10, it might have rank 9n over 10, or somewhere in between. There's at least n over 10 to the left, n over 10 to the right. Okay, so now the question is, can I take a terrible median algorithm, one that's like, could still be off by almost half the elements, okay, and still try to convert that into a good algorithm for selection? Can we do any ideas? Yeah. Okay. Okay, I hear you. But just to go a little bit slower and help me as a teacher, what would the algorithm be? Great. So let's just look at the same algorithm again, right? Your subroutine returns an approximate median. You compare everything again, n time like before. It might not be so balanced this time, right? And you recurse on the appropriate half. So same algorithm, just that your median's not perfect. You do need to, last time you always knew your element was n over 2 right in the middle. This time, as you do the comparison, you need to figure out what its rank is so that when you recurse on the appropriate half, so this might be rank some L, right? L is somewhere between n over 10, 9n over 10. So if you recurse on the right side, you need to go to k minus L, whatever L is. L is not necessarily n over 2. But by the time you've done this dividing into two sides, you know exactly where it is. So L is easy to get. Okay, so going a little bit slowly, uh, this is the part, right? So as you divide the input, you also figure out the rank of the thing you found, since it's not given that it's n over 2. Okay? So you just have to be a little bit more careful about your recursive calls and updating your rank. If you go slowly, nothing surprising, but if you go fast, you might skip this detail. Okay, so then here's the interesting thing, right? Well, this same algorithm, same basic algorithm, will still give us a good running time. So first, let's model the running time. T of n is what? Bounded above by. Yeah, so in the worst case, you're still getting rid of 1/10 of the input, and then you need to spend some linear time processing the thing. Yeah. And then the recurrence tree, again, not very interesting. Things are going down by a factor of 9/10. So forth, right? And the work is the same. And 9n over 10, 9 over 10 squared n. Yeah? So we just have to figure out what this all adds up to. Okay? Okay. So you're looking at a sum that looks like this. Yeah, so instead of 1/2 to the I, you have 9/10 to the I. And so what is this? Huh? Yeah, it's like roughly 10n. So in general, any constant that's less than 1, you can even make it go all the way up to infinity. Okay, so arbitrarily close to 1 to the I is just going to be a constant. Okay, as long as that number is a constant. If that number is like 1 minus 1 over n, then you get some weird things depending on n, but that's not the case here. If it's a constant, you get a constant. And in this class, you don't have to worry about which constant. Yeah, you just get, oh, it's a geometrically decreasing series, I'm done. And then we'll move on to the next problem because that's more fun than calculating the constant. But it would be like roughly 10. Okay, yeah. Yeah, the 2tn over 2 makes a big difference. And when we wrote the recurrence tree, each level was contributing n, which means we also, so it wasn't decreasing. and geometrically decreasing, which means we also have to be careful about how many levels there were because each one contributes n. Here, I mean, it is true that there's not that many levels because it goes down pretty rapidly. But even if I assume infinite number of levels, the 9/10 squared cubed fourth that won't add up to much. Okay, good, good. So that's just something to keep an eye out for. You get a geometrically decreasing sequence, you're done. You're just done. Okay, good. So we know if you can get an approximate median, you can get anything. Yeah, but now you just have to figure out how to do an approximate median. And maybe the nice thing is that this seems potentially easier than the original selection problem, right? Selection is pick any arbitrary element out perfectly. And here it's saying getting an approximate median. Median is almost like the easiest case of selection at some level. It's like kind of symmetric. I mean, I guess the extremes are easier, but it's just one particular point. And you're allowed to make tons of errors. All right, so yeah. Okay, I'm not sure how to make the next part like rhetorical, but any ideas? Yeah. Okay, yeah, it's a great idea. We won't formally do much randomization until later, but I can still explain the suggestion, right? So you're looking at like the middle 80% of the input, but it's arbitrarily sorted, so you don't know which one's which. But if I pick a random one, I have an 80% chance of it being in the 80% middle. Yeah, so I'll pick one randomly, and then I'll do all the comparisons and see if it was in the 80% range. And if it is, I'm happy. There's my approximate median. And if it isn't, okay, I'll try again, right? But you're going to be correct like 80% of the time and wrong 20% of the time. So it's like how many times you have to keep flipping a coin until you get heads, except the coin is even slightly more in your favor. So in general, for a fair coin, what's the expected number of coin tosses until you get a heads? Two. And if I told you the coin flipped heads is probability 10%, 1 in 10 times, what's the expected number of coin tosses until you get heads? Don't be shy. Okay, 10. So, and that'll probably show up in your homework later. I'll have to delete it now. But that's not so hard to work out on scratch paper. Maybe I'll still have you do it once. Yeah, but we won't do that because it's only week 2 of the class. But that is a good idea. Yeah. Oh, okay. Can I try to select something small? Can I try to select one of the extreme ones? But if I gave you an extreme one, for example, it's very easy to find the minimum element, right? Just scan through and I get the smallest one. What would you do with it? Yeah. Okay, so yeah, let's say you did select and you got, so the idea is like, can we somehow use select and get one of the extreme, maybe the extreme ones would be easier or something, right? And let's say you did select and with, n over 10 and you get, uh, oh, okay, but why would n over 10 be easier? Okay, so is the algorithm you have in mind, you get the n over 10 smallest element and you can throw out everything smaller? Oh, okay, but then we still have to figure out how to implement select n over 10. Let's say k is already n over 10. Yeah, but how do you get the n over 10? But that's 10 as opposed to n over 10. I think you're going to run into a little bit of trouble. So can you somehow take advantage of like, okay, you really want to focus, you're saying that can we focus in on this special case? But what would you do here? Okay, so this is the thing you're trying to implement. We're just trying to do n over 10. Oh, we're trying to implement approximate median. Let's hold that thought, maybe come back to it at the end, see if, yeah. Oh, okay, if I can take, interesting idea. Okay, so here's 20% or n over 5. And then if I get the median of this, then I'll be able to throw out, if I get the exact median of 20%, I should be able to throw out 10% one way or another. That's the idea? Okay, that's actually kind of interesting. So, okay, so at some level, it looks like we have something like this. T of n is equal to, let's say, exact median on n elements, and I'll write S of n to be approximate median, the time for approximate median on n elements. And let's see how this works. This is actually a pretty interesting idea. So we're trying to implement approximate median, and the idea is to do t and look at 1/5 of the input. And I guess that's it. But you might need O of n time to assemble. Okay. And then on the flip side, we have an algorithm that runs in Sn over 5 uh, plus big O of n. Sorry, S of n. Okay, something like this. And that means if I plug things in, if I substitute in for S of n, we get something like this. This looks, okay, I know what I did wrong. Okay, there is a bug here. I did something wrong here. Okay, so S of n represents, I don't know. I'm trying to implement approximate median of exact median. Yeah, there's a bug here. So to get the exact median on n, you get an approximate median. Let me rewrite this. Let's just do exact select on n. Sorry. It's a little messy, but I'm, running with the idea. So I made a mistake in my modeling when I wrote S of n plus big O of n. So that's saying, okay, to do a select, I'm going to do an approximate median plus linear work. But what would the algorithm actually do, right? So I'm trying to get a median or some select, and I get an approximate median, which is ultimately going to do this 20% exact median of this. And I had to do some linear time to do some comparisons. But then, okay, there's still a t of 9n over 10 that I forgot to write down. Okay, so now that's from recursively, once I have the approximate median, I could throw out some stuff and I still have to keep going. So if I plug this back in, if I just substitute in for S of n is equal to Tn over 5, so I can put everything just in terms of t, I'll get Tn over 5 plus T of 9n over 10 plus big O of n. Okay? And one thing that's going to be a little tough, I'll work in a smaller space, is when I start writing the recurrence tree, I'll get one problem of size n over 5 and another problem of size 9n over 10. And then down here, I'll get like n over 25, and I'll get 9n over 50, 9n over 50, and 81 over 100, so forth. And we know that each of these subproblems is contributing work corresponding to its own size. So I just have to add up these rows. So this is going to be like n. This is going to be like 1/5 plus 9/10. I'm sure you guys can do this faster than me. 11/10, they say. Yeah. What would be the next row? Yeah. There's an easier way to see this. It'll be 1/5 plus 9/10 squared, which you can see happening in the tree, right? It's really just doing the factoring in the tree for you. And going all the way down, you're going to get 1/5 plus 9/10, to the in on the nth level. Okay. There'll still be log n levels because you're kind of, making some progress. Although it'll be a weird constant. But okay, so that means you're going to be your overall running time. I'll pull the n on the outside. So h is going to be like log of 10/9 of n ultimately. Sorry, I usually ask, but I'll put just h here. That's the height of the tree. Okay. Uh, h. Okay. Sorry, I know it's a little chaotic. Uh, but ultimately you get this 11 over 10th to the I for every level, and there's h levels. Okay. Where h is going to be roughly log n, but it's really log 10 over 9 or something. Okay. And each time the worst part of your tree is going down by a factor of 9/10. So what does this come out to? O of n log n. Okay. Anyone else get n log n? Sorry? Yeah, the sum was going forever. These are all bigger than 1. In fact, they're getting bigger than 1. So this could be a large sum, but there's some limit h, which is log base 10 of 9n. But we can just use h for this answer so that you don't have to do this mouthful. How do you deal with a geometrically increasing sequence? Sorry? No, there's a limit. It goes up to h, where h is like log of n. Yeah? Oh, okay. So 11 over 10 is awkward. What if it was 2, right? 2 plus 4 plus 8 plus 16 plus 32. Yeah. Yeah, but what's the formula for finite geometric sum? So it's going to be dominant. Oh, if it was powers of 2? Yeah. So in general, the geometrically increasing sequence is always going to be dominated by the largest term. Okay. Always dominated by the largest term up to some constant. The exact formula will get you the constant in front, but you're always going to get n to the, up to some big O, 11/10 to the h. Okay. I can't get rid of the h because h is a function of n. Yeah. And you'll get n times 11 over 10 log to the 10/9 of n. Yeah. And this is sort of a pain to deal with, but how would you deal with it? Huh? Put a what? So let me, sorry, I'm not doing a great job of space. Uh, All right, so we have n 11 over 10 log base 10 over 9 n. I would love to get like n to the something, right? I like having n in the exponent with some log is like, what the hell is that? So let me do the lazy thing. I'm going to write n, and I'm going to write 11/10 as 10 over 9 to the log base 10 over 9 of 11/10. That's just the like definition of log base something, right? And this is raised to the log base 10 over 9n. Yeah, but now what's convenient about this? Now I can bring the n down, right? Because it's 10 ninths to the log base 10 over 9. And when they multiply in the exponent, you can swap them, right? Okay, so you get n to the n comes down. So you'll get 1 plus log 10 9 11 over 10 or something. Yeah, and this is where you bring out the calculator and just figure out what that number is. But clearly, like, that's more appealing, right? You have the n down below, you're going to get some constant, whatever this log is, and you'll get n to the 1 point something. Yes, that's how you deal with it. Yeah. Because there's 1 from here, so this is really n to the 1. Uh, or let me put it this way. I could have written it like this, n times, and then this part is coming from this where I bring this n down. But there's always this n here. Shouldn't the right half be? Yeah, so what I'm going to do is I'm going to take this and this and swap, right? Something like this. And then that n just goes down and becomes n to this messy number. Yeah, yeah. I mean, if it's confusing, it's probably because of my handwriting. Yeah. Okay, so that was look at this mess. Um, you have to be there. Okay, so but this is a very interesting idea and also a very natural idea, right? Why don't I take the median of a smaller subset of my input, and that would be an approximation for the whole input. And I think that's actually a fantastic idea. But as it happens, that particular idea, when we wrote it out, we got this n over 5 plus 9n over 10, and if you did a million recursion trees, your eyes would immediately go to the fact that n over 5 plus 9n over 10 is bigger than 1n. Yeah, we got that 11 over 10, and that's when we got this geometrically increasing sequence, and that got us to actually a worse running time than sorting originally, but that's not so important. Yeah. But that's a very good idea. In fact, what we'll do is quite in this direction. But any other ideas? Not that we have white space for it, but any other ideas? We can always make space. We have the technology. All right, so this is a very creative and celebrated algorithm. Okay, with celebrated authors. Uh, so it's by Blum, Floyd, Pratt, Rivest, Trojan. I should have wrote the year, but I think it's the 70s. 70s. Anyway, 4 of those people have won a Turing Award, and the 5th one basically founded Sun Microsystems. So this is a lot of pedigree behind this. And the real question is, would you rather found Sun or get a Turing Award? Okay. Um, so Pratt was the Sun Microsystems guy. And okay, so here's the idea. Okay, it's not so different than trying to get the median of 20% of the input. Okay, we're going to be just a little bit more clever. I'm going to take my input A, I guess I'm calling it A, and I'm going to divide it into groups of 5, like contiguous groups of 5. Okay, and get the individual medians of each group of 5. Okay, so that's going to reduce my input to n over 5, which is exactly what we were doing before, reducing to 20% of the input. But we were a little bit more subtle about which 20% we picked, right? Because these are like kind of in some small way medians in their little adorable ways. Right? Okay, so I'm going to take all these little medians and then collect them into an array, again, 20% the size of the original one. Okay, but they're a little more selective than before. Okay, and then I'm going to get the median recursively of this set. Okay, like this looks a lot like what we just did. We are taking 20% of the input and getting the exact median from it. And the only difference is how we chose the 20%, right? And somehow we must have done something different if I'm going to get a better running time because we just analyzed the previous one, right? So there must be some observation that gets us ultimately to a stronger recurrence. Okay, so good. So here's the claim, okay? So that we're going to actually do better than a 9/10 median. Okay, we're going to get like 3/10 on either side. So the claim is that if you do this median of medians, instead of being between in the middle 80%, you can get in the middle 40%. Is that correct? Yeah, 3n over 10, 7 over 10. I think that's the middle 40%. Okay. Which means when it comes to your recurrence, instead of decreasing your input size by 1/10, you're going to be able to decrease your input size by 3/10. So that 1 over 5 plus 3 over 10 would be like what? Or 7 over, or sorry. So if this is true, then our recurrence is going to look like uh, there's some big O of n work, but we got the median of 20% of our input, right? And now the remaining input is at most 7/10 the size, if this claim held. Okay, so clearly 7 over 10 is smaller than 9 over 10. That's good, but something critical happened in particular. Yeah, so n over 5, or 1/5, plus 7/10 is 9/10. So we have it later, but when we do that recurrence tree, we're going to get 9/10, and it's going to go down. Okay? So somehow this small tweak, and you can get a stronger approximate median. It's going to make a world of difference. Okay, so how do we prove this? Okay, so I'm going to, for simplicity, assume the input is divisible by 5 first to sketch the ideas, and then you're just going to be off by plus or minus 2 at the end, if you go through it a little more carefully. Okay, so what I've done is a proof by picture. I mean, you could do it more painfully, but we're going to do a proof by picture. Okay, so I've sort of organized the input so that each group of 5 represents one column. Okay, and in this picture, I've reordered those columns or groups of 5 so that the green row of our little medians is in sorted order, in increasing order. Okay, and I've also sorted the rows so that they're in increasing order. Okay, so for the sake of the proof, I've kind of rearranged things in a convenient way. Okay, so that means our median of medians should be middled in the median of the green, which in sorted order should be in the middle of the green. Okay, and I think that's where it's drawn. So now what we'll do, so we want to argue that like roughly 30% is smaller. Okay, So in this whole input array, first, which ones are clearly smaller? Okay, so we know these ones are smaller because they're smaller inside B. Yeah. Yeah, and above it. And then smaller than all of these, which actually you have to go up. That's the only reason, only way you know. But this is bigger than this, bigger than this. This is bigger than this, bigger than this. So you know these are smaller. And now you can see that it's 3/10 of the input. Yeah, it's 3/5 of the left side, and the left side is 1/2 of the whole thing. And then on the flip side, okay, which ones are bigger? These are bigger. These are bigger. These are bigger. And that gives you 3/10. Yeah. In actuality, there may be like, okay, that won't work. Uh, there may be an array of size 3 or size 2 or size 1 left over, and that's only going to shift things additively by a couple. Okay, but that's the idea. Okay, so very cute, right? Yeah. So median of medians is this whole diagram, and it's going to call exact median just on the green part in the middle. So we're going to first do the baby medians, which I should note are very easy to find, right? You have a group of 5, you just look at it and you figure out the median. It takes constant time to find a median in any constant number of elements. So to prepare the green part, we'll take linear time total, because you only have to do medians of groups of size 5, so very few comparisons. And then you're going to extract out a slightly smarter 20% of your input and get the exact median from that. Yeah. This is a little tricky because we actually kind of went to another algorithm before we brought it back recursively. Yeah. Yeah, exactly. So it takes 5 log 5 time, which is a constant. Yeah. That's right. I think there's people who have like, you can be very clever, I think, with 5 about like getting it down to like 2 or 3 comparisons. And I think people have like actually written a paper about this, but I don't care. Yeah. Okay. Um, Good. So that's the proof. Right. Well, I've already said it, but still, I'll force you to say it again. How long would just this subroutine roughly take? Or how would you model it if finding the median takes t of n time? Okay, whatever. It's going to take tn over 5 time plus some linear work. And again, here's the pseudocode, which I think just makes it look harder than it is. Okay, so I won't distract you too much with it. Um, okay, so let's go slowly through what we already did out loud. If I were to model the running time, it would be, sorry, it's not just this. This is too good to be true. Or you're missing one more term. What are we missing? The 7n over 10. Did I already have that prepared? No, that's okay. And when you start plugging this in, 25 is too much math for me. Okay, n, right? And then you're going to get 1/5 plus 7/10 times n. I guess I should do this. So what's 1/5 times 7/10? Okay, 7 over 50 is not that bad. 7 over 50, 49 over 100. Okay, but really this is 1/5 plus 7/10 1/5 plus 7/10 squared times n, and so forth. And so you're going to face something like this: 1/5 plus 7/10 to the I times n. You've already done this, right? This is 9/10 to the I times n, and you get your linear running time. Yeah. Yeah. So if this was 3, the question is why 5? If this was 3, what would you get? Oh, doesn't the 7/10? Uh, that's true. 7. Okay. The shortest answer is it works. 7 also works. You have to check if 3 works. Well, it might be a small constant, but then your little groups of 7, you're doing a little bit more work there. There'll be a constant there. So I don't know. Sorry, what? Okay. I mean, at some level, you got linear running time. That's saying you look at the input once. And I can't imagine doing it without looking at the input. So you're not going to improve things by more than a constant. Moreover, in practice, do I have? Yeah. In practice, this actually isn't a great algorithm. Okay. Well, the fastest algorithm in practice is similar to the randomized one we did before, but even simpler. I'm going to pick a random number, split it into two groups, and just recurse on the appropriate group. Even if that random pivot I picked turned out to not be that great, oh well, I'll still go into that and recurse. Why not? You still get a few. Yeah, that's called quick select. That's much faster in practice. So as yeah. But when we get to randomization, we'll have a more nuanced idea of worst case. Yeah, because in fact you can prove you'll never ever see n squared. You'll get struck by lightning like 100 times, and then 100 times more, like long before. Yeah, it was very high probability. Yeah, but we'll get there when we have the tools. Yeah. What matters is that it's worst case with respect to the input. Like you're on average, it's going to take linear time, no matter the input, which is what we really care about when we do algorithms, right? We want to make algorithms that work from any input and get guarantees for any input, even if the running time is average, but that average holds for any input, right? So slightly nuanced notion of worst case. Yeah. So I wouldn't worry about this like, oh yeah, you get the worst possible coin tosses. It wouldn't be that great. That won't happen because they're coin tosses. But well, that's a bigger discussion for later. Yeah. Perfect. Yeah. The n over 5 comes from the select inside median of medians. Other questions? Okay, good. All right, so let's do another problem because that's what we do. So this one's going to be geometric. Okay? So I'm going to give you n points in the plane. And, the distance is going to be like, the difference in the x coordinate squared plus the difference in the y coordinate squared. I guess I chose sort of a confusing notation here, but x1 minus y1, that's the difference of the two first coordinates. And then x2 minus y2, that's the difference in the two second coordinates. Yeah. So this is just Euclidean distance, right? Pythagorean theorem kind of stuff. Okay. So your goal is, well, I chose this notation where it's a matter of notation. Here, x is equal to x1 comma x2. and y is equal. Yeah. So when I say x coordinate, y coordinate, that wasn't like the perfect terminology. Yeah. It's a tradition in computer science to make things as confusing as possible. Okay. But you get the idea, right? So I just want to get the closest pair of points, and so I'm not sure what the closest pair would be. Maybe this pair of points looks pretty close. It's some distance delta. It's like I don't know, this much of my thumb. I guess it's bigger up there, so I don't know how you look at it. Um, but that's the idea, right? So what would be like the easiest way to do this? Yeah, just try every pair, in a big for loop and just measure, 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 measure. Yeah. And how long would that take? That'll take n squared time. Okay. And the question is, can you do better? And obviously we're going to do better or else I wouldn't. Yeah. Okay. So, but does the question make sense? I give you endpoints in a plane. You want to find the closest pair of points? Yeah? Okay. Um, good. You can imagine this being practical in lots of cases. Okay, so, all right, I tried my best to try to build up to the idea. So I thought, okay, what would be simpler? What if the problem was in one dimension? I give you a bunch of points in one dimension, or, the second coordinate is always zero or something. What would you do? Yeah, so you have to sort to get it on the line first. Here it looks like it's already sorted, but in general it won't. And then you can just measure, you can just sort and scan, right? So that's a good idea. But I don't know how to generalize this to two dimensions because I don't really know how to sort in two dimensions. So that's a good idea, but we're going to try to do something different. What would be maybe out of the way, but a second approach to trying to do this in linear time? Yeah. Yeah, absolutely. So once the points are sorted, there's a lot of redundancy. You definitely only need to compare the adjacent points. So I think this is what I meant when I wrote scan. Sort the points and then scan. You only have to compare the comparison. Oh, well, if I give you the points just as numbers, you would still need to first sort them in order so that you can figure out what's the next point. Here I've drawn them as if they're on the line, but in general, your input's going to be like a list of numbers. They might not be in order. And then the first thing I do is sort it and make it, yeah, so the picture's a little misleading in this regard. But then once you have it, then clearly, yeah, you should only be looking at the neighboring points. And the only that's a great idea, except in two dimensions, I can't imagine an analog to sorting. I'm going to give you a bunch of two-dimensional points, floating in space, and it's not clear that I could sort them by one coordinate from left to right, but then, you know, it's tricky. Then the next point on left to right could be very high, very low, or something. Yeah. Yeah, but the question is, what does next mean? How do you figure? Okay, so idea was for each point, figure out the closest point and measure it. Of course, that would be great because whatever's the minimum distance over all points is going to be the closest for those respective pairs as well. But that's going to be a little tough. If I give you a point and say, what's the closest point? Like that might be harder. Yeah. no, these are all good ideas. Let me, just for the sake of whatever is prepared, let me suggest the, yeah. So, okay. Can you expand out and do kind of neighborhood queries and do a search? Um, Possibly, but it will go into a different like data structure direction. So you can try to do these circular range queries, but you actually have to do a transformation to some other, it gets tricky. Uh, Rectangular queries don't quite help you, right? Because it doesn't capture diagonal wells. You can generalize binary search trees to do two-dimensional binary search trees and do rectangular queries. Um, but you're worried about these diagonals. They don't quite match the circles are more natural, right? For what we want, since we're doing Euclidean distance. It is true that you can do range queries with circles, but there's a trick where you kind of map it to a different geometry so that rectangles in the other geometry correspond to circles in the original one, like some linear algebra transformation, which I kind of forget the details of. That is possible, but I'm not prepared to. Anyway, it's not going to be divide and conquer. But it's not a bad idea if something does exist. Okay. But let me suggest another approach, which is sort of clumsy and heavy-handed, but would also get linear time. Okay, but it doesn't explicitly sort. You can try to get the median x coordinate, right, and split the input in half, and get the minimum distance on one side, the minimum distance on the other, and then I'm only missing the cross distances, right? But sort of analogous to what was just suggested, I should only have to compare the furthest point on one side and the points that are hugging the boundary from either side. So just one more comparison. So, okay, the suggestion is this might generalize better. Okay, so here then is I don't know if that's very believable. Anyhow, here's the actual algorithm. Okay, so step one is we are going to split at the median x coordinate. So here's our points in a plane, and you're going to split the median x coordinate. Okay, so that's like I guess where I drew the median. Okay, and now you're going to recurse on both sides. Oops. Okay. So this seems like somewhat of a standard setup. I've split the input in half and I've recursed. And you look at one side and you say, maybe this is the closest on this side, and maybe this is the closest on the second side. And it looks like delta 2 is a little smaller than delta 1. So I'm going to say that I'm going to call delta to be delta 2 because it's the smaller of the two. Okay. And now here's the part where things get subtle and you might be able to guess. So now the only issue is I'm missing the cross pairs, right? I'm not comparing one point from the left side to any points on the right side. And I want to do better than comparing everything completely. So what are some ideas? How can I, yeah. Okay. So at some level, right, if 2 points across the boundary are going to be smaller than delta, then each of these points need to be delta close to at least a boundary, because we need to get across the boundary to get to delta, right? So I can draw like two sort of things of width roughly delta. Okay, it's not perfectly vertical, but and so these are supposed to represent width delta, right? So we can look at this vertical band of width, I guess 2 times delta is what I wrote, but delta on each side around the median. And then try to just do the comparisons in between, right? Somehow this is sort of unspecified, but just try to focus on these narrow bands and do the comparisons between there. Clearly those are sufficient, or I hope it's clear that it's sufficient, because any pair that's not in the band is going to be distanced more than delta because it needs to, yeah, or if even one of them's not in the band, you already lose delta distance just going across the band. Okay, so that's the high level idea, but at some level, like, okay, if you look at this picture, it feels like there's not too many points in the middle. right? And maybe one can just like march down from the top and just like, okay, I'll first look at this and look at the next couple down this band. And maybe I'll move to this guy and I'll look at the couple down here, right? And, I probably don't have to compare all the way down here because that's pretty far, right? So in this picture, it looks like there's not that many purple points in the middle and that not too many comparisons are required, right? Especially because like I know that this thing here should only have to look inside a square, you know, of side delta or something. And it feels like the delta size squares are like not too dense in this picture, right? Still, maybe that's just a nice picture. What prevents us from having tons of points inside these bands, right? So something really bad is I have tons of points inside here, inside just, all endpoints are inside here or something, right? And so I end up having to spend just as much time looking inside this narrow region. Yeah, I mean, I can't make purple dots forever, but what, yeah. Ah, okay. As I start stuffing purple points in there, then even if I look on just one side of the blue, it's starting to get pretty congested. It's starting to get crowded. And at some level, delta would have to shrink. They have to be delta apart, right? So what does that suggest? What are we leading up to? Yeah. Yeah, so delta or more. But at some level, like, okay, let's look at this point here, right? And it needs to compare itself to any purple point on the other side, but it's only like within, y-axis delta of it. Beyond delta, then it's already so far away on the vertical axis, it's not a big deal. Yeah? Yeah, I mean, well, you're only worried about points within delta distance. So I'm imagining on this point, and I want to make sure I kind of compare myself to everyone outside on the other side of the line. But I shouldn't have to look too far, right? I don't need to look more than delta horizontally, and I don't have to look more than delta vertically, and I don't have to look more than delta the other vertically, right? Delta down. And if I can argue that like, so in other words, this region, maybe I should use a different color. This region is like really where I want to make sure that I am comparing myself to everyone in that region, roughly of size delta. Yeah? Yeah, so if I can argue that there's only a few purple points that I can stuff into that critical region for that point, then I should only have to compare myself to like four other points or something, right? Because only so many candidates can fit in there. So that's going to be the idea. So, okay. Oh, this is a little redundant. I'll go quickly. Right, so it's very narrow. The distances are pretty big, and you're hoping that not many comparisons are needed. Okay, I'm summarizing what we just said. Okay, so I guess I chose 10. I'm not sure why, but what I'm going to do is I'm going to sort all the points by vertical coordinate initially, so I can just kind of go down the list. Okay, and as I go into, maybe I should go through the code a little bit more slowly. So P1 is everything on the left, P2 is on the right, and then I'm letting P3 be everything on either side that's in this small band. So you already figured out everything on P1, everything in P2. You just have to do P3, okay? And I'll list the points in order. The first top point, second point, third point, fourth point, fifth. And this code is saying, look, if I'm at the fifth point, I only need to compare myself to point 6 or point 15. 10 is some conservative number. You could probably get it down if you wanted. Okay, but saying each point needs to only compare itself to the 10 next points. And then beyond that, it should be safe to ignore. Okay, so that's what the code's going to try to do. I'm getting some confused glances. Okay, so I was lazy and I'm not even doing the like, oh, make sure left compares to right and right compares to left. I'm just going to sort them, collect them all in the middle. Yeah. Why? Yeah, yeah. So if I sorted it, it would take n log n. That's absolutely true. So how can I avoid sorting? Yeah, so first of all, this is a relatively small point because if there's an extra log there, we still get like n log square n, and that's much better than n squared. But to get rid of this sorting in the middle, what you can do is at the very beginning of the entire algorithm, before doing anything, sort all the points by y coordinate, vertical coordinate, and then keep that order as you go and do your stuff so that when it comes to this stage, they're already in order. Yeah. Okay, good. Okay, so to that end, to prove this algorithm works, you only need to look at 10 points. Here's the claim. If I'm at some point A, okay, and I know that everything on the right and the left are, delta apart, right? And so if I go delta to the right, delta to the left, and I go down delta, and I look at this square, the claim is that there's at most 10 points inside there. Okay? And that's why we came up with 10, and we could probably do better than 10 if we wanted. Yeah? So I think it suffices, so to just look at one side. Oh, maybe that's sort of gives it away. Okay, so I think it suffices to just look at one side, and any constant is fine for the sake of discussion. Yeah, if you got 20, okay, you did 20 comparisons in your code, whatever. So I just want to look at one region and try to argue there can only be, okay, so this is squares of size delta or something like this. You could do 2 delta or something. And I want to argue that you can only stuff a limited number of points in there if all the points have to be delta apart, which I think is totally intuitive. Yeah, but then how do you prove it? How do you get a proof written down? Yeah. Oh, that might be better than whatever I had in mind. Okay, I could divide this into small parts. Okay, and now we want to argue there can be at most 1 point from each quadrant. Okay, so the furthest I can do is I guess I can do opposite corners of one of these smaller quadrants. And what would their distance be? Sorry? So it should be like root delta over 2 squared plus delta over 2 squared. Did I do that right? And so you're going to get something like square root of 1/2 delta squared. Did I do that right? There's 2 1/4s. And this is less than delta because of that 1/2. I think that works. Okay, good. That's clever. I'll tell you then my relatively clumsy proof, just because this sometimes is useful in other scenarios. So one kind of packing argument is to say, look, any point here is going to carve out a ball of radius delta over 2. It's a little small, isn't it? So the radius will be delta over 2. Okay. And so it's going to take up some amount of volume, pi times delta over 2 squared or something. So all these points, these balls have to be disjoint, right? Radius, because they're delta apart, so they're delta over 2. And they all fit inside a slightly larger square where I add delta over 2 padding, like margins to the side, right? So you're trying to stuff these disks of radius delta over 2 inside this slightly bigger square, okay? And this bigger square has area 4 delta squared, right? Because it's going to be 2 delta times 2 delta. And each disk has area uh, pi r squared or something. So pi over 4 delta squared. And they're disjoint. So you just take the big area divided by the small area, and that'll tell you how many disks you can fit in. So that's a volume packing argument, which is sometimes useful. Okay, but actually, I think this four quadrants thing is much more direct and probably better. But that would be a different approach, is to do this area thing. Okay, good. So once you establish that, so that means instead of 10, it could be like 8 or something. Um, that's your algorithm. Yeah, you proved that you don't have to compare that far down the list. Oh, okay, good. So, okay, I'll only mention at the end, how do we model the running time? What will be the running time? Yeah, so the two recursive halves are give you two Tn over 2s, plus the rest of the work is O of n, especially if we don't have to resort things. And we've already done this recurrence. That's n log n. Okay, yeah. Finding the mean is O of n because we've already shown, yes, O of n. Mm, what was the running time of the algorithm from your the question is n log n a lower bound. Do you remember the algorithm from your final or midterm? There's some, I think there's a faster randomized algorithm that uses some funny operations. If you're allowed to do like rounding an integer down, like rounding down n over 2 or something in a single atomic operation, then I think you can get O of n. And I think that was on the randomized final or midterm, as Peter clearly seems to remember. And made quite the impression on him. Okay, so actually, so this question is actually a little bit funky. I I should have known the answer, but I'm not sure. You can definitely Google it. Yeah, the question was, what's the lower bound for this problem? But there is a faster randomized algorithm with one weird arithmetic operation, which is a little dubious, maybe. Okay, anything else? Okay, so next time then we're going to try to multiply integers faster than we normally multiply integers. And we're also going to do something cool called the fast Fourier transform. Yeah, which is relatively cool. Okay, whatever. All right, I'll see you guys next time.